Alright, so for today's pre-lecture video, I wanted to go over one of the conceptual questions that we did Monday in class and do a little bit better job of presenting it. And then I want to spend the rest of the time just introducing you to a concept about how if work is done in a magnetic field. Okay, so in our problem, for this conceptual question, we're talking about ions, and they're accelerated through a potential difference, and then they go into a magnetic field. And basically, we want to compare the radius of the two different masses. How do they compare? The first thing that I wanted to talk about was the idea of the potential difference and what relevance it has to us. Accelerating through the potential difference is how the masses acquire their velocity. And so we start with the idea that the change in potential energy is equal to minus the change in kinetic energy. This is the idea of conservation of energy. And basically what is happening is you start your particle at a higher potential, and then it's going to move to a lower potential. And the reason it would do that is because this would also be the direction of the electric field. If you remember, the electric field points in the direction of decreasing potential. If you take a positive charge in an electric field, it's going to experience a force parallel to that electric field, and that's the way it's going to move. And as it's going to do that, what's going to happen is you're going to also have a change in potential energy. Now, so the idea, remember, that potential energy is related to Q times V. So when we talk about the change in potential energy, let's talk, and we'll say that this is position 1 and this is position 2. So first, let's just rewrite it down here. This is U2 minus U1, and just to be fair, the change in kinetic energy is K2 minus K1, with that negative sign there. The potential energy it has at the end is Q times V2. Potential energy it has at the beginning is Q V1. We could write this as Q times V2 minus V1, which also could be written as Q delta V. However, because of the fact that we understand that it started at a higher potential and went to a lower potential, we need to remember that this quantity is, delta V is less than 0. And so this whole quantity is also less than 0. And so the delta U is a negative quantity, and that's why it makes sense for it equal to minus the change in kinetic energy, because what's going to happen is the particle is going to end up with some final velocity, but it started from rest. And so because, again, this is a negative quantity, the signs all match up. So we have delta U equals minus 1/2 mv final squared, but this is negative. We can write it as Q delta V and 1/2 mv final squared, negative, and this is negative as well. And that's sort of, I wanted to sort of show you that the signs do reconcile, and I was a little careless with that the other day. This tells us that in general, the final velocity can be expressed as 2 times Q times delta V over the mass. Now, we can make some conclusions about the speed of the two particles based on that. The velocity of the smaller particle is going to be the square root of 2Q delta V over big M. The velocity of the larger particle is going to be the square root of 2Q delta V over 2m. If I want to compare them, I could say, if I look at these expressions, the velocity of the large particle is 1 over the square root of 2 times the velocity of the small particle. And that's because of this 2 right here. And so that's something that I want to keep in mind as well. So now we're ready to talk about the radius. Starting with QVB, that's the force on the particle, is equal to mv squared over r. That's using the idea that the force is equal to the mass times acceleration, and the acceleration is centripetal acceleration. I think it's always good to start with this step because that means we don't try to memorize all the different expressions for radius and angular frequency and cyclotron frequency. It's just not necessary. So from this, I can find that the radius can be expressed as mv over qb. And now I'm going to just remind us that the velocity of the small particle was the square root of 2q delta v over m, and the velocity of the large particle was equal to 1 over the square root of 2 times the velocity of the small. That was the result we had from the previous page. So now let's look. The radius of the small particle can be expressed as mv small over qb. The radius of the large particle, I can first start off, is going to be 2m, velocity of the large particle, over qb. But then I can substitute in this expression, so I can write 2m, 1 over the square root of 2, velocity of the small particle. So all that I've done is I've substituted in for the velocity of the large this expression over qb. And so if I think about this expression for the velocity, the radius of the small particle, I notice that those terms are in here. And so when I'm looking at the radius of the large particle, if I take out m, velocity of the small, q and b, what I will be left with is basically 2 over the square root of 2. So then this is just the radius of the small and times 2 over the square root of 2. And so this is giving me a relationship between the radius of the small particle and the radius of the large. Since we're running out of room, I'm going to write it again. So I get the radius of the large particle was equal to the radius of the small particle times 2 over the square root of 2, which could also be written as the radius of the small times the square root of 2. And so then finally it asks what is the radius of the lighter, so I'm just going to solve for the radius of the small, and it'd be 1 over the square root times the radius of the large. I think that was more organized than the other day, and hopefully you'll agree, and at least it makes a little bit more sense to you. Now, the next thing I want to do is I want to talk about whether the magnetic field can do work on a particle. Just reminding us, work is the dot product of force times displacement, or for a small displacement, we can write an increment of work is equal to the force dotted with the small displacement. Now, reminding you that the force due to a magnetic field of a particle that's moving through the magnetic field is given by this cross product, and we found that this means that this force is perpendicular to the velocity and to the magnetic field. So that means because as my particle is moving, ds will be parallel to v. And so then we could say that the force of the magnetic field, because it's perpendicular to v and ds is parallel to that, it will also be perpendicular, that force, to the small displacement. So when we're thinking about work for the force on a charge in a magnetic field, FB dotted with ds equals 0 because they're perpendicular. So it doesn't do work. The answer to this question is no. Furthermore, remember that work can be found to be equal to the change in kinetic energy, and so this also means that the particle in the magnetic field will have a constant speed. And that's because the kinetic energy doesn't change, and so that means the speed is constant. It does not mean the velocity is constant. Remember, they're different. And so when we look at this object, this particle going in a circle in a magnetic field, because of the fact that the force doesn't do work, that means then that the speed is constant. And it's just an interesting fact that didn't really seem to be coming up, and I wanted to make sure that you knew that. So hopefully this is helpful. See you soon.